Hey, good evening, guys.
Hi,
Hi, Volker. How are you doing?
great.
Hey, Matt. I wanna allow you to talk, but it says you have an older version of Zoom.
Who, me?
Oh no, Matt. But I can promote Matt to panelist. So let's see. Uh, Matt, can you give me an audio check? Hmm. Yeah, Matt. I don't know why, but for some reason I can't enable you to share audio. Maybe you have to unmute on your side, unless you don't mind, unless you don't want to participate in the. Okay, my view looks different now. Yep. So you're now a panelist, and in theory, you should be able to share audio and video. Okay, that looks better. Matt, I think you're good now. You want to give me audio check? I think you're muted, but I've on my side you have all permissions. Okay, I'll let you figure it out. If you need my help, just let me know. Um, okay, in that case, we'll just go ahead. So thanks a lot for joining, guys. I'm pretty excited about today's session. So today's SPV clients, that's the first topic, and payment channels and routing. Yeah. Okay. And if we have time, yeah, I prepared one slide on Submarine Swaps because the L&D guys, our Lightning Labs, published a new product or service where they allow you to add liquidity through Submarine Swaps. And so I sketched up a quick slide on that. And if we have enough time today, it'd be cool if we could cover that as well. But as a prerequisite, obviously, payment channels and routing need to be covered before that. And that would cover session 7. And then if we can get everything done for session 7, we can use session 8 to do review of any topic you like. So I'll ask that question in the Slack again later, but please let me know what topics you'd like to cover or review again, or dive a little deeper into for our last session, final session, number 8. Okay. No questions from last time. I'm going to kick off with SPV channels. If there are, just quickly let me know. No? Okay, cool. So SPV channel, SPV clients, I'll make this as brief as I can. It's quite a, let me see. Sorry, Pierre. Sorry, you guys came a little later. So I got Bitcoin Kempton and I got Pierre, who just joined.
So,
Pierre,
hello.
you should be on audio now. Same goes for Bitcoin Kempton. You guys real quick.
So, do you hear me?
Yep.
Okay, great. Thank you.
Awesome. Okay. So SPV clients were mentioned in the original Bitcoin paper way back in 2008 or 9, 2008. And SPV stands for Simplified Payment Verification. SPV, the idea of SPV is if I am a client and I want to verify that my transactions were confirmed, I can make a certain trade-off. And the trade-off goes as following. I do not verify double spend. I do not explicitly verify that a transaction that I'm confirming is double spending. However, what I do verify is that the header chain where my transaction is confirmed in, that header chain is correct, that the proof of work that's been performed or produced there is correct. And the underlying security that assumption in SPV clients is, although I don't check for double spend, I don't produce a valid, I don't parse the entire blockchain for a valid transaction history, making sure that no transactions ever double spend. However, because double spending would be so expensive, that's the assumption, the cost involved in creating a branch, a double spend branch, that is longer than the main chain branch, because the cost is so prohibitive, I assume that there is no double spend taking place, because otherwise the miner would be creating an invalid chain, which would be rejected by all fully validating nodes which check the transaction history. Okay, so SPV wallets do not check transaction history, or clients do not check transaction history. All they do is check the proof of work, which is captured in the headers. So the first thing a SPV client does is it does header chain validation. So what does that mean? That means it downloads or it obtains all the headers, right? Those are 80-byte data objects, and it will validate them one by one. Now, how does it validate a header without the transactions? So it doesn't. What it does is it checks that the header points to the previous header. So as we saw last time, one of the header fields is previous header hash or previous block hash. Those are used, that term is often used interchangeably. And for each header, I can compute a certain chain state. Now, the chain state means that there is a certain difficulty at that height that's computed from the previous headers. And that allows me to determine whether the proof of work is correct, is valid. Okay, so as I move up the header chain, I don't download any transactions. I don't verify any transactions. I just make sure that I'm following the header chain with the most proof of work. And I want to make sure that the proof of work that every header has is in fact valid according to the retargeting algorithm which I apply. Again, the retargeting algorithm looks at the previous 2016 blocks, looks at the timestamps of the current block and the one 2016 blocks ago, and make sure that the average block interval is at 10 minutes. Okay, so we validate the longest header chain, and that's the first part of what the SPV client does. Now, what does the SPV client usually want to do? SPV client usually wants to make sure that that a transaction was correctly sent to it, meaning a transaction with an output that this SPV client can spend is somewhere committed in one of these headers, right? In the strongest or in the strong header chain where there's the most proof of work. So that is the that is the how should I say? So in order to be able to, okay, let me show you from a point of view of a client, what are the steps that the client needs to do to verify that a transaction has been received, containing an output that it can spend. So first thing it does, we already saw, it makes sure that it obtains the header chain with the most proof of work. Because of the cost of creating this chain, the SPV client assumes that this chain is correct. It does not validate the transaction history. There could be double spend in there, but because the double spend would be so prohibitively expensive, the SPV client assumes that it is correct. In a second step, the SPV will need to obtain information about when or what block the transaction it is interested in is broadcast or confirmed. The SPV client can obviously monitor the P2P network. That's one way to determine whether a transaction has been broadcast, that has an output that it can control, an output or an address that it can control. But the SPV client cannot look into a block directly itself. The SPV client does not have a UTXO set, right? So it cannot check into the it cannot obtain a transaction and check in the UTXO set whether it's a valid transaction. It can't perform that validation. All it can do is obtain from a full server, denoted query service here. It can obtain from the full server a notification that a transaction has been confirmed, and that transaction sends to an output which the SPV client can spend. Furthermore, it needs to know the height as well. So it needs to know the height where this transaction is confirmed. Now, given the height, what the client will then do is verify that the transaction that is interested in is in fact committed to the Merkle root within that header. So from a full server, it now needs to obtain the full sequence of transaction hashes that are committed to that header. Here, header 3. So just to repeat quickly, it's waiting for the transaction. It's subscribing to some kind of notification that from our full node server that tells it at that height, in that block, your transaction is committed. In a third step, it now obtains all transaction hashes which are in that committed to the header. Again, that's not information that the that's not information that the SPV client itself can verify, where these are very valid transactions. However, it can obviously create the Merkle root, construct the Merkle tree and or Merkle root, and then the Merkle root, and compare that with the header that it is stored locally in its strong chain. So by being able to verify that the transaction that it's interested in is indeed committed to that header, and together with the fact that it is expensive, it is provably expensive to fork or create a competing branch that is stronger than the header chain it currently obtains, because the cost is so prohibitive, that is the underlying security assumption that the SPV client relies on. So no UTXO, it doesn't build a UTXO set from the chain history. It doesn't verify double spend per se. It doesn't have the ability to do so. But with a much lighter and much performant chain of, or lighter chain of data or chain of headers, it can verify that the transaction hash has been committed to a header of a certain height. Okay, and so that's it. That's the basic idea of SPV clients. A lot of mobile apps may work like this. To be frank, a lot of mobile apps just speak directly with a full node server, and so that's those are the two ways how you can create a light client that can verify transactions, incoming transactions. The headers can be obtained, as I said before, either directly on the P2P level. So the client can find P2P peers, handshake, start outbound, inbound channels, and obtain the header chain that way. Or it can directly query a full node server service, like Libbitcoin or your local RPC, JSON RPC from Bitcoin and obtain the header chain from there as well. So there are multiple ways you can do that. Okay, so that's SPV clients. Any questions? Pretty simple topic.
Can you hear me, James?
Yep.
All right. Yeah, I have a question.
Sure.
So, SPV client, if it needs to, basically doesn't have UTXOs in it, so it needs to basically, how does it know, I mean, on this picture, this says transaction to be validated on the right. Pay expense from SPV wallet. It doesn't know exactly the transaction which basically happened some time ago. It knows that there are some outputs there which you might have. And how does it basically compare? How does it know that the TX hash 2 is the correct hash? I mean, how does it know that TX hash 2 contains unspent outputs, which it wants to spend?
You're right. It needs to have a copy of the actual transaction. In fact, it doesn't. It doesn't. Let me restate that. That's incorrect. The SPV client needs to obtain a full copy of the transaction, or else it will never know that the output is spendable by the SPV client.
I mean, how do I do? I mean, if it's a light client that doesn't have any UTXOs, how does it know? How does it know exactly the transaction which happened some time ago?
So the SPV client will first need a notification from the full node server that there is in fact some transaction that it is interested in. So at this point, the SPV client doesn't know anything. It just knows there's a transaction that the server is telling me I can spend that output of that transaction. Then it obtains the height where that transaction is committed to, the height of the block where that transaction is committed to. It obtains the sequence of all hashes inside that block, and it also needs to obtain from the server the transaction that the transaction that spends to the SPV client. If it does not obtain the transaction that spends to this SPV client, there's no way for the SPV client to determine that this output, in fact, is something that the SPV client can spend. That output must be, yeah.
So basically, it gets not only those hashes, and it also gets the complete transactions from.
It must have the complete transaction. Otherwise, it would be, if it only had the, if we can reverse the idea, if it only had the TXID, it is trusting the server that this TXID belongs to a transaction that it can spend. There's no security.
Okay.
That's zero.
Thank you.
Yeah, exactly. That's a good point. Okay. Okay. So if there are no questions, let's go into payment channels. So, oh wait, actually I have a couple. Let me make some comments on the examples on SPV clients in the exercises, which I think are worthwhile. So there are 3 examples here demonstrating the 3 parts of what an SPV client needs to do. It needs to build a header chain. It needs to watch for an address or watch for a transaction that spends an address to be able to then perform the Merkle tree or Merkle root verification that we saw before, which is the 3rd part. Okay, so these are the 3 things that an SPV client needs to perform. The first one, I have a SPV, I have a C++ example here. So this is with the Libbitcoin system and Libbitcoin protocol. And the ZMQ stuff, is just native to Libbitcoin server. So the Libbitcoin server communicates through a ZMQ interface. And so here we're just setting up the ZMQ socket. Thinking out loud, in fact, if we have enough time next session, I might do a quick intro on how to use the Libbitcoin server from your application's point of view, because it uses these the ZMQ messaging framework, which is actually really good, very performant, and very easy to use. Okay, next, what we're doing is we are using the chain state class from Libbitcoin, and the chain state class behaves very identical to what we described before. Sorry, it literally just captures the proof of work targeting state, if you will, at every height. And then the nice thing about chain state in Libbitcoin is the way it's implemented. The retargeting state is updated at every height. So what I mean by that is the retargeting only occurs every 2016 blocks, but that doesn't mean that when you do the retargeting, you have to perform some kind of backwards lookup, right? It doesn't mean that at every 2016 blocks, you need to perform some lookup on a block that 2016 blocks ago. Instead, what you can do is you can take the chain state and you can promote it incrementally from one height to the other, and it will automatically roll over the retargeting at the correct height. So that's really nice. So we initialize it. I'm not going to go into too much details here, but so besides the retargeting, the other thing that it also captures are protocol activation, update activations at certain heights. So there are a couple of bits that activate at certain heights, or are inferred from, their activation is inferred from a certain chain height, and this class also captures that. Okay, and yeah. So for every height, what we do is, so I've limited to a certain height because it's otherwise it would go on for quite a while. But we're basically just fetching the block header at every height, and this is all the ZMQ stuff I'll show you guys next time. But we're creating a ZMQ message according to a certain format, and we're querying it for a certain height, and then we send it out over the socket. We submit the query, and then there's a certain response which we then parse. Again, we'll talk about that format next time. That's not too important. But the point that I'd like to show here is what we do is then we verify two things. We verify, first of all, that the subsequent header is always pointing to the previous one, right? So previous block hash must equal received header previous block hash. If not, then obviously there's a hash link that's broken at a certain height. Then we verify proof of work, and there's a nice method in the header that does that for us. And we can also, this is the integrity of the bit encoding of the header difficulty. And then we can verify the proof of work based on the chain state, right? Which is what we're doing here. And so then you print out at every height whether we're printing received header hash and the target. And let's run this for a second, see how it works. Okay, so when we run it, you see it'll continuously make queries at every height. There is a header hash. There's a target printed out. And as you see, obviously the header hash will always be below the target value. And let's see if we can see the retargeting occurring. Okay, so yeah, this is not a very good example in terms of how you should do multiple queries, because I'm doing it synchronously. So request, reply, request, reply. So every round trip overhead is yeah. Okay, so it's taking too long, so I'll quit it. But you will see after a certain while that the retargeting occurs, and you can visually observe that the header hash, obviously, in order for it to be valid, will always be below that target. Okay, so I'll start this right here. Okay, and then we have the watch address example. Okay, let's go real quick. And here, I think this is a nice example. So let me just restart and clear our examples. What we're doing here is we are subscribing to a notification from the Libbitcoin server for every transaction that spends to a specific address, right? So for every address that is confirmed, we will get the hash and we'll get the block height. We need the hash because we need to then query for the full transaction. And we need the block height because we need to then verify whether the transaction is actually committed into the Merkle root of that block. Okay. So again, this is all about taking an address and then decoding the pub key hash from it for a pay to pub key hash address. And then that's the hash that we'll use to make our notification subscription. So this is just ZMQ stuff. I'll talk about that next time. Renew address subscription. Okay. So you subscribe. I'll just give you the basic gist of it. You subscribe to a certain address. You do that by submitting the pub key hash that you're interested in. And the notification may or may not come depending on whether that transaction is ever broadcast. And so in order for the confirmation subscription to stay alive, you periodically resubmit that subscription request to keep that subscription alive. Otherwise, it'll be canceled on the server side. Yeah, so that's nice because that's another ZMQ feature. Being an asynchronous messaging framework or protocol, it allows you to do these subscription-based kind of things. Okay, and finally, once you have obtained a subscription or notification that there's a transaction that spends to your own address, you can then create or construct your Merkle root. And the way we do it here is we obtain, let me skip to the relevant parts. We obtain the transaction hashes at the relevant heights, and you can use it using the fetch block transaction hashes method, query that from the server. That will return all the transactions that you'll need. And then you verify that the transaction is first of all in that list, the transaction you're interested in. You also query the transaction. Do we do that here? We actually don't do that here. But as Dimitri mentioned before, you would definitely need to query the actual transaction from the server. So you want to verify that the output is in fact spendable by a key that your wallet controls. And finally, we build the transaction block. Sorry, the Merkle block, or the tree, if you will, down here. Okay. So there is a Merkle block class. Let's see, where is that? Oh, actually, there may not be a Merkle. I may be mistaken. I thought there was a Merkle block class, but here I'm just using a hash list. No. Okay. But in any case, yeah, you just construct the Merkle tree. As you see here, at every level, if the number of hashes is odd, you duplicate the last element. And then once you reach once you've constructed the Merkle root of the tree, you can verify that that is equal to the one that is actually committed into the block.
Sorry.
Yep.
So I ask for a receiving address,
Mm-hmm.
and therefore I become eventually a transaction.
Yep.
And then I have to ask for the left side or the right side of the Merkle tree routes.
Yeah.
So that I can compute the Merkle root.
Yeah. So if you look at the server interface of Bitcoin Core, you can request the Merkle path. So it will return to you not the entire tree, but only the nodes that you need to reconstruct the path from your transaction to the root.
Yes. So I ask the same peer who send me the transaction.
No, you can ask any full node that is willing to provide that service to you.
Okay. Yeah. Thank you.
Yep. So you can ask any trusted server that you want to obtain that information from. And the Merkle path or the Merkle it would in theory be possible for you to obtain the entire block over the P2P network, but in effect, I don't know any client that does that. Most clients, SPV clients, communicate exclusively over a client-service interface. So there's a trusted server or a list of trusted servers, and they communicate over a server-client interface, not the P2P network. There's certain things again that you could obtain over the P2P network, like the header chain, transactions, the block transaction hash list. You could do that. That is possible. Yeah.
So it's different from the peer-to-peer network. I have to do another connection by its own.
Yes.
Okay.
Yeah. It is possible to build a SPV client that only obtains all information through the SPV through the P2P network. That's possible. Like the newer, I think it's called the Neutrino client. That does everything through the P2P network.
Okay. Yeah. Okay. Thank you.
Yeah, but again, there's certain trade-offs that happen there. Obtaining things over the P2P network is relatively slow. You have certain discovery time. So once you start your P2P node, you need to discover active nodes. You need to connect to them. So there's a certain connectivity overhead that you have, which you don't have when you have a simple server-client interface. But the neutrino client does that, and as you can check yourself, when you run the neutrino client on your phone, for example, it's relatively slow. It takes a long time for it to sync. Yeah.
Okay, thank you.
Okay. Okay, so on the payment channel side, I have two parallel decks which I've used both. One is the one that is very close to the one that I use in my videos. So I like to use that because it's a little easier to get into. But if everybody has seen the videos and doesn't want me to review that again, I can go to the more detailed ones. So what do you guys think? Both, or you don't mind the repeat, or you want to dive into something a little more detailed, or we just do both? Both. Okay. No worries. So I'll start with the more high level deck, and it starts with payment channels, and then we go from payment channels into routing. So payment channels are what Lightning is based on. Payment channels have been known for a while, or have been conceived for a while, and payment channels are uniquely between two peers, two payment channel peers. And the idea of using payment channels is we want to be able to transact between these two peers without having to actually broadcast or confirm transaction on chain. Obviously, confirming transactions on chain provides security, but the trade-off is obviously cost. I need to wait for the transaction to confirm, and for higher values, so let's start with the lower values. For lower value transactions, the fee that I need to pay may be prohibitively high, which makes the transaction uneconomical or reduce the utility of that transaction to zero. The thing with Bitcoin on-chain is the minimum security I can have is one confirmation. There's nothing between no confirmation and one confirmation. The fee that gets my transaction confirmed depends on the transaction size in weight and bytes. It is independent of the amount being transferred. So at a certain value that I want to transfer, the utility of the transaction on-chain necessarily becomes zero because the fees are potentially higher than the value that I want to transmit. So that's where layering comes into play. Layering allows me to cache or combine multiple transactions off-chain, and allows me to increase the utility of the, if you will, the combination of all these off-chain transactions into fewer on-chain transactions when I open or close the payment channels. In effect, what I'm trying to do is I'm trying to capture updates to the off-chain balance, and I want to capture that in a way where I do not have to transmit or confirm any on-chain transactions. So in a very simple example here, I have two participants, A and B. Remember, payment channels are always between two parties. And as we move ahead, all that we want to do is we want to update the balances between these two parties. And the updates can go in both ways. So as long as A or B has a non-zero balance, that party can transfer funds to the other party. And with every transfer, all we need to do is we need to update the balance state. So from balance 0 to balance 1 to balance 2, as you can see, there is a transfer that occurs because the balance between the two states is different. We also want to have a way to be able to take the final balance and to be able to transfer that into spendable Bitcoin on the Bitcoin network. The problem with payment channels is because it's only between parties A and B, what happens if A and B want to take those funds and transact with other people who are not in the channel? So that necessarily becomes something that both parties will eventually want to do. They want to take the balance. They want to be able to convert that into spendable UTXOs, which are confirmed on chain. So we want to design some kind of protocol that allows us to do this, right? That's the goal of payment channels. So in order to be able to do the final step where we took the payment off the off-chain balance, and we transformed that into on-chain spendable UTXOs, we need to necessarily have a funding transaction. Otherwise, we would be creating UTXOs from nothing, right? The UTXOs must spend from something, and it spends from a on-chain confirmed funding transaction. So this funding transaction provides the funds with which the two parties transact in the channel. So everything below this line here is implied as something that will be confirmed. It's a transaction that's on-chain, that's confirmed at some block height. Everything above this line implies a balance that is only negotiated between Alice and Bob. It is not something that's reflected directly on-chain. In fact, it is invisible to any observer who is validating the Bitcoin blockchain or is monitoring the P2P network. Okay, so we have a funding transaction. It is funded, let's say, by 2 participants or 1 participant, and there's a certain multi-sig output that is only spendable by both participants. This multi-sig output is necessary because as we'll see later, as we then ultimately convert this output into individual UTXOs spendable by Alice and Bob, that ratio of outputs, that ratio of output amounts is negotiated between A and B. And since it's negotiated between A and B, it only makes sense that this output is a multi-sig output because it requires the agreement of both parties to be able to spend. So let's look at how this works. So I have a funding transaction, and that funding transaction is then spendable or spent by a commitment transaction. This commitment transaction is nothing but a channel state. It reflects the current balance, and that balance is captured in the outputs. The first output is spendable by Alice. The second output is spendable by Bob. So from this, we can infer the channel is funded in equal parts by Alice and Bob, and the initial balance is 500 each. And both of these needs to be signed during the channel opening, because if we didn't sign the commitment transaction or the child transaction, then this multi-sig output would eventually be locked if Alice and Bob did not agree on spending it. Okay, so if we sign or we create both transactions together, both parent and child transactions, we can be sure that if the funding transaction is confirmed, that the output A and B can be spent anytime, because all that needs to be done is to have the commitment transaction be broadcast subsequently. So in terms of the sequence events, both funding transaction and the first commitment transaction are signed. Only the funding transaction is broadcast and then confirmed. And once it's confirmed, the payment channel is now open. Okay? It is now open. And because we didn't broadcast the commitment transaction, even though it's a valid one, we can update it. And that's the fundamental idea of payment channels, Lightning Network, and all layering protocols that are based on this concept. Because these commitment transactions are not broadcast, they can be updated as many times as you or the participants would like. And every update, as you can see here, needs signature A and signature B because it's spending a multi-sig output. Because it needs signatures from A and B, it needs to be negotiated by both, right? It is an agreement by both parties that there is a new balance in this payment channel that's reflected too with the outputs. Now, both parties obviously store a copy of this commitment transaction, and as it's updated, the updated commitment transaction will still spend from the same funding output. And if any party wants to close the channel and walk away, all that needs to be done is to have the most recent commitment transaction broadcast confirmed, and these outputs will now be spendable on-chain. As you obviously know, the problem here that we have is any of these old commitment transactions are still valid. They're signed with correct signatures. However, they reflect outdated balances. So the payment channel that we have currently is pretty useless because it cannot enforce that only the most recent balance is broadcast on-chain. So there's something that we need to fix here. But before we do that, there's one more thing, and that's transaction malleability. And we talked about it at the beginning with SegWit, but transaction malleability was a problem and prevented payment channels from being possible before SegWit or segregated witnesses were introduced. And the reason is the following. In order for a child transaction to spend from a parent transaction, the child transaction will always point to the UTXO or the output with a tuple. That is the transaction ID and the index. The transaction ID is derived from the parent transaction data. And if the parent transaction data is malleable, the TXID will be malleable as well. Malleable means I can alter the data of the transaction without altering the validity of the transaction. So before SegWit was activated, the input script and the input script and also signatures were malleable, and that meant that a transaction could be confirmed under a different transaction ID because the input script could be modified in flight or by any adversary, thereby rendering the commitment transaction invalid because it is pointing to the wrong TXID. So in such a case, the funds would be locked in this output, and this rendered the entire protocol pretty useless. Now that we have witness transactions, the malleability is solved because the input script data is now moved all to the witness data. The TXID is not computed with witness data. Therefore, the transactions have become no longer malleable. Okay, so now payment channels protocols, as we have constructed in our example here, they work okay. Okay.
So question, James.
Yeah.
Is this your example with the funding transaction? Is this an example of a dual funded channel, which is not really the reality yet on Lightning, right?
Yeah, it's not a reality on Lightning today. And although there's no reason for them not to, there's no reason for a payment channel. So when I say payment channel, I'm kind of just generalizing. I think we can be more specific in the second part where we talk about Lightning or routing. But generally speaking, a payment channel, a payment channel is not unique to Lightning. So, anybody could come up with a payment channel protocol today and their own payment channel network, if you will. And if you were to create a payment channel today, you could, without any problems, create a dual funded payment channel protocol. There's nothing about the Bitcoin script system. There's nothing about the Bitcoin consensus rules as it is today that prevents you from doing it. The reason why they didn't include it in the first Lightning version is it requires a little more interactivity when you create between the two peers. And there is the problem that one peer will receive the full funding transaction, and that peer can become unresponsive, and the other peer on the other side will then have to sweep the funds of the UTXO that it provided for the funding transaction. And that sounds a little complicated, but I have one slide towards the end where I'll go over that again. But long story short, the reason why the reason why it wasn't included is from a UX point of view, there is a, if you will, an exception that you have to catch, meaning that if one peer becomes unresponsive at a certain stage, the wallet or the Lightning node has to sweep that UTXO. But they are, it's for, I forget for which version, but it, in their meeting in Australia, Adelaide last year, it was on their roadmap. So it will come sooner or later. It's not really a missing feature of Bitcoin that prevents us from doing it. It's more of a UX problem that needs to be solved, namely when one peer becomes unresponsive. So Antonio, I'm sorry, I'm probably not answering your question all too great, but there is one slide on dual funded channels that hopefully makes that a little clearer later on.
Yeah, so does the issue with having inbound capacity versus outbound capacity, is that related to the fact that these existing channels on Lightning are not dual funded?
Absolutely, 100%. So if I can only if I can only initiate a channel where I have all the funding on my side, I have to wait for somebody else to connect to me before I have any liquidity that's inbound, right? Okay. Whereas if I could find, I could negotiate a dual funded channel with the person I'm connected with, I would have both inbound and outbound liquidity with just one channel versus having two, right? But yeah, as Lightning Lab guys announced yesterday or today, with Submarine Swaps, you can provide a service where somebody routes you liquidity back in return for an on-chain payment. And I have one slide on that towards the end, and maybe we can follow up on this question there as well. Okay. Okay. So in our current example, we still need to find a way to make old commitment transactions revocable. We need to find a way to cancel them in a sense, so they can't be broadcast, and so an old state can't be confirmed, thereby basically revoking the latest transfer on the payment channel. And right, so these are all valid. And the way to solve that is with a revocable sequence maturity contract. That's just a Bitcoin output script, a little complicated one. And it needs to do two things. So it needs to obviously be able to be spendable by the local node. And I'll clarify what I mean with the local node in a second. And it also needs to be spendable by the other party if it is revoked. So as you see here, again, this is the everything below this line is confirmed transactions. Everything above the line is signed but not broadcast. These are stored locally on the peers. And now we have a certain asymmetry that's introduced here. We have a transaction that that peer A holds, and we have a transaction that peer B holds, and they are not identical. Okay, and the output that spends to the local node is the node storing this commitment transaction, that can be revoked with a secret and spent by the remote node. Okay, and before we dive into how the contract actually looks like, suffice to say, given that it is revocable, cryptographically revocable, we can now revoke older states and make them sweepable if they are broadcast. If somebody tries to cheat and broadcast an older state, that output is revoked and can be spent by the counterparty, as we see here. Okay, I'd like to have a closer look at how these RSMCs look like. So here's an example of a revocable sequence maturity contract. Yep, thanks, Volker. See you later. Thanks for joining. And this is the output script of this is the basic Bitcoin script that is underlying this output, this revocable output. So you have two conditions. You have the first condition where it is spendable by public key R. And this is the revocation spend scenario. And then you have another spend scenario or condition where after a certain delay, it's spendable with the signature to this pub key, right? You have a checksum here and the pub key here. And I like to just quickly go into how this revocation secret is generated, or how this cryptographic revocation mechanism works. So it works like the following. You have, before this output is actually created, each party generates a secret, which is a scalar, right? EC scalar. And none of these secrets are exchanged. The pub keys, however, are exchanged. Okay, so the pub keys are exchanged, and the pub key R, which is captured here, is nothing but the sum of these two pub key points, right? So as we can see here, the secret required to spend this pub key is the sum of the two secrets which each party generated specifically for this output. And each party, so party 1 has R1 and party 2 has R2. And so if I want to revoke this output, all I have to do is reveal my half of the secret to the other party. If I reveal my half of the secret to the other party, then the other party can compute the entire revocation secret and can then spend this output immediately with no delay before, in this case, before peer A can then spend. So that's how the revocable sequence maturity contract works. Again, the first spending condition is the revocation. Revocation happens when one party reveals its secret to the other, and after a certain timeout, the output can also be spent by the local node, in this case, peer A. Any questions on this?
I just have a basic question, technical question. What the op if does? I mean, how does this logic work in this script?
Yeah.
When the first clause triggers and when the second clause triggers.
Yeah. So it's the conditions for op if and op else. The argument that op if and op else consumes or validifies or verifies, the argument is on the first element of the stack. So let's consider the input script here, for example, signature A and 0. Let's pop signature A. Let's run through this real quick. So I take signature A, I push that into the stack. Then I take 0 and I push it onto the stack. Now the top element on the stack is 0, right? So now we go into the output script, and op if is going to evaluate the first argument on the stack, which happens to be 0, right? So because it's 0, it's going to go to op else. If this were 1, then the top stack element would be 1, and op if would evaluate to true, thereby executing this branch here.
Right. Okay. Yeah. Sorry, I kind of missed the right part. So, but that explains it. Thanks so much.
Yeah. So all you have to do is just provide that 0 or 1 in your input script. That's all it is. Really quite straightforward. Okay. Let's see where I was. Okay. So now we can revoke outputs. If revoked outputs are barcast, we can sweep them. And I talked about this in my video a little bit as well, but I think this is worth repeating. So what are balances in payment channels actually, right? Can I equate payment channel balances to Bitcoin? And strictly speaking, you cannot. So a UTXO that my wallet controls, that has, let's say, 100 confirmations, has a lot more security than the same amount in a payment channel, which is still open. And the reason is because a payment channel balance is a signed transaction that is not confirmed yet, right? It could possibly be the case that both nodes either lose this commitment transaction, that you lose it locally, and the counterparty broadcasts in valid state, and you don't have the copy to be able to revoke it or to sweep it. So in a way, it is a security trade-off, which you are willing to take for transfers with very low fees, right? So again, a balance in a payment channel cannot be equated to spendable UTXO on-chain because it has no confirmations. These are unconfirmed transactions. The balances that you capture in your payment channel are in transactions which are unconfirmed. Okay, and the second part, the second observation that we can make about payment channels is the following.
Sorry?
Yep.
Because you mentioned the fees. Who has to pay the fees in case of a closing transaction?
Who has to pay the fees in case of closing transaction?
So to open a channel, it is clear.
Yep.
It's always the person who opens the channel.
Yep.
But I don't know who pays the fees if the channel closes.
So the fees are negotiated at the point where the commitment transaction is signed, and the fees, I forget the formula, but the fees are deducted from both participants in that sense.
Okay. So so both participants pay the fee no matter how the closing transaction, no matter who spends the closing transaction.
Correct. So the signing of the transactions occur before the transaction is broadcast, and so there's a certain fee forecast that or fee assumption that you make. That fee assumption could be wrong when the broadcast time or the closing time actually occurs. But there is no additional fee that's added when you broadcast. At least not today. That could change. As of today, the fees are already fixed at the point of signing the commitment transaction.
Okay, so if I force close a channel, the two participants have to pay also.
Or in a sense, they've already paid. If that makes any sense.
Yeah. Okay.
Yeah.
Understood. Yeah. Thank you.
Great. Okay. Let me run through this real quick. So for the payment channels, because it's an off-chain balance, I like to differentiate between confirmed, unconfirmed transaction, and negotiated channel balance. So the negotiated channel balance is a, if you will, it's a construct between the two peers. It's negotiated. The signed commitment transactions are a way to anchor this balance in potentially confirmed UTXOs. And so what that means is the actual channel balance can be denominated in a different unit than you can on-chain. So, the Lightning protocol, for example, we have millisatoshis, and obviously there's no such thing as millisatoshis on-chain. The smallest unit of denomination on-chain is satoshis. So what will occur is for a given channel balance in millisatoshis, the two nodes will round them. They will agree on a rounding to the closest satoshi. Now that rounding can benefit one party over the other, but it is an agreement, or it's a balance it's a conversion from the balance to output amounts that is agreed to by both parties. It is agreed to by both parties because these transactions are signed by both parties. So mini satoshis in that sense are a negotiated balance. However, it cannot necessarily be accurately transferred to on-chain outputs. Right? That's just something I wanted to mention. The advantage of having millisatoshis is to be able to transfer funds off-chain in a unit which is smaller than what is possible on chain. So I can have milli-Satoshi transfers. A milli-Satoshi transfer may actually result in no change in the rounded outputs. That could be possible, right? So that transfer, in effect, will have zero security because it's not reflected in the outputs. But it could be that so the advantage, though, nonetheless, is over time I can nonetheless create a lot of milli-Satoshi transfers, which in aggregate obviously will be captured and rounded to the closest Satoshi amount. So that's just a subtlety that I want to mention here. The channel balance denomination mustn't necessarily be equal to the output amounts in the commitment transactions. Okay, let me skip to, if you guys are interested, I have a example where we build a payment channel with BX. And it is quite simple. We are doing nothing, but we are basically just creating transactions. And the transactions all have the same revocable outputs as we saw before. So we have a funding transaction, and every box here represents a transaction that we will script with Bitcoin Explorer or BX. So we need to create output, a multi-sig outputs, and we need to script a RSMC output for these transactions here. And so it follows the same a sequence of steps that we saw previously. And the part that I wanted to show you in particular was the RSMC script. So this is the RSMC script that we now need to encode in Bitcoin in BX. As you see here, we're creating a revocation secret with both Alice and Bob. And the actual RSMC script is then captured here. The public key R is the sum of the two public keys generated by both peers. And the pub key here spends to the local node. Okay. So as you can see, all we have to do is create this RSMC output script and then build the transaction accordingly. And thereby, we can construct a commitment transaction that is revocable, with simply with the BX command line tool. So that's pretty neat. But the actual process of building these transactions is almost identical to all the transaction exercises that we saw previously with BX. Okay. So let me move on here. Okay, so the next part, let me just double check if I covered everything here. So this is the same payment channels. Okay. So the next part is about routing. So in Lightning, obviously, we have the ability to route funds across peers which are connected through channels. The payment protocol that we've seen so far only captures balances between two peers. So we need to find a way when we route funds across multiple peers that this can occur in a way which is atomic, right? Because what we don't want is this payment routing, let's say from D to Alice. We don't want it to start somewhere and then suddenly fail in between, because then we'll have a incomplete routing from D to Alice. We want it to occur atomically. So let's see how this can happen. So here we want to, I showed it in the wrong direction. So here we want to route funds from Alice to Dave. And as we can see here, the economic incentive for any intermediary node to participate is a certain fee. And that fee is reflected in the amount that's being transferred from peer to peer, right? So every peer will forward the payment in its in the payment channel, and that amount will be necessarily lower than the previous amount, namely by a delta which reflects the fee that node obtains. Okay. So again, we wanted to create this routing in a way which is atomic. We want to coordinate this routing across multiple hops, and the way to do it atomically is as follows. So what D does is Dave will create an invoice, and in that invoice, you will find a payment hash. And that payment hash has a certain preimage to it. That payment hash is forwarded to Alice, and Alice can now construct a special output. We'll call those HTLCs in a second. But what Alice can do is Alice can try to construct a lock for the funds that she wants to forward. And she will then forward this payment hash to Bob and Charlie so that they too can lock temporarily the forwarded amount. Okay? So we are trying to create an intermediary state where the forwarded amount is locked in a temporary lock, and this lock mechanism allows us to release all funds in an atomic fashion later on in the second step, thereby making the routing process an atomic routing process. So let me introduce one more thing in between. The process to create these temporary locks in the outputs in the commitment transactions is through a messaging protocol which obscures the route along all intermediate nodes. So we don't want Bob and we don't want Charlie to know where the originating node is and where the final destination node lies. And the way that happens is through a onion routing message protocol. So that's kind of shown here. A is the only participant who knows of all nodes along the route. A will create a specific private key, or will create a specific pub key for every node along the route. And that specific pub key is called the ephemeral pub key. And that is used in Diffie-Hellman to create a shared symmetric key with which that specific encryption layer is done for every step. So for every node, A will create a dedicated ephemeral pub key, here for B and C, for B and for C and for D. And because it is a pub key used in a EC Diffie-Hellman shared key process, only B will be able to decrypt that layer. Okay, and so by encrypting the information that each node needs to forward that message and to create these payment locks, Alice will be able to encode these pieces of information layer by layer, allowing each node to unwrap one layer and to forward the remaining encrypted part to the next node. So B, for example, will find out the node that it needs to forward to, the amount that it needs to capture in this temporary lock, and it will also forward to C this ephemeral pub key, which C needs to be able to decode its layer of the onion packet. And this is how the information then propagates all the way to D without each node knowing exactly the entirety of the route. But it provides each node with information so that it can then create the correct lock for the funds that need to be forwarded. So before I continue, let me ask if that makes sense, if there are any questions.
I mean, it makes sense. I just have a question, which is kind of not quite about what we're talking about. But how does A in general calculate the path to D in Lightning? I mean, A usually assume. I mean, A knows the whole topology of the network. I mean, is it what usually they do, or
yeah,
in practice?
In practice, there's this gossip protocol. So the channels, if they want to be public, they can gossip their capacity and the channel state to their peers. So it's a gossiping protocol. But of course, it doesn't reflect the actual available liquidity. So a routing can necessarily fail if the liquidity is not there.
So basically, my Lightning node has the map of the whole network at all times.
It has a local view of the Lightning network. It does not have since it's a P2P network, it cannot possibly have a complete view. It has it has the view that's constructed from messages that propagate to it. But there are as many topology states as there are nodes in a P2P network, right? If I have a central server, let's say I have a central coordinator in Lightning, which we don't, that central coordinator can tell every client what the current topology is, and we'll all have the same topology state, even if it's out of date. But if you're all on a P2P network, every node has its own view of the topology in that sense.
I mean, if it doesn't, for example, doesn't have an index of all the nodes in the network. For example, somebody gives me an invoice. I need to pay it over Lightning.
Yeah.
And I look at my table and, okay, this address is not there. So what do I do now?
Oh, the actual routing algorithm? Actually, I don't know if it's different from implementation to implementation. I don't know. So your question is like how to compute the most efficient route.
Oh, any, not even like just some of them. Yeah, I mean, most efficient would be nice, but any route.
Yeah, I don't know the specific graph traversal algorithm that's being used. Yeah, sorry, and I don't think it's in the. It's not in the Bolt specification because it's not a protocol. It's an implementation. You would find it in the implementation of LND or C Lightning, but I haven't looked into it. Yeah, sorry.
Thanks.
Sorry, I don't know the answer to that. Okay, so I'll move on a little faster. Okay, so we're talking about lock with which we want to lock the forwarded amount, and that's kind of represented here. So whenever we construct this route, and now we have negotiated that, yes, indeed, we can construct a route from A to D, the amount that we want to forward is temporarily locked in a new output and hash lock. And that's reflected here, as you see in the output scripts. So the outputs of the commitment transactions. You can also notice that the amounts are decreasing because there's a fee that's being subtracted at every hop. And in order for us to now complete the routing, all that Appear needs, for example, is the pre-image and that to that payment hash, and this output can now be spent by day, for example, right? So once somebody broadcasts a transaction and spends the output, the pre-image will necessarily be in the input script, and everybody can see that. So the pre-image is now public to other peers along the route as well. Thereby, since we're using the same payment hash along the entire route, peer B and peer A can also close the channel and spend this output with this pre-image that's being that's in this input script, which is confirmed on chain. Okay, or we can refrain from closing the channel, and the pre-image can be propagated backwards. And as it's propagated backwards, both peers in the channel can then negotiate that this amount be absorbed into the receiving peer's balance amount, right? So we get rid of that hash lock output, and the amount is then absorbed into the receiving node of each channel. Okay. So this slide was about why does it have to propagate backwards? It has to propagate backwards because if we were to propagate the pre-image forward, B now has obtained the funds and has no incentive to forward it, right? So that's incentive problem. So that's why the pre-image must always propagate backwards. So a node will never obtain the forwarded amount before it actually has to forward it itself. Okay. We also need time locks because otherwise what can occur is the node D may never actually reveal the pre-image. The receiving node D in the routing might never reveal the pre-image. And if that is the case, there is no way for these outputs to be released. The funds cannot be released because they're in a hash lock. So we can simply just introduce a time lock in addition to that. This time lock ensures that this output will time out, and this amount is then paid back to the originator in each channel. So this amount here will be paid back to B. This amount here will be paid back to C if the timeout expires after a certain time period. these timeouts relative to each other also need to be decreasing. And the reason is the following. So imagine if they were not decreasing, but increasing, what can occur is that this output here can expire before this one. So this output here could expire before this one. And therefore, the amounts are returned on this side of node C. But on this side of node C, the funds have now been forwarded to Dave. So node C has now lost the full amount that was to be forwarded, and never received it from Bob. Right? So that's why the timeouts need to be decreasing in decreasing order and not in increasing order as shown here. Okay. Now we're going to dive into HTLCs, and this gets a little heavy, but it's worth going over. So we now generally talked about what the HTLC needs to do. It needs to lock funds and be spendable by a pre-image, and it also needs to be spendable by the originator of the channel after a certain timeout. Okay, so these are the functions that an HTLC contract needs to be able to fulfill. Now, we also need to introduce a way now to have the HTLC be revocable. Why does it need to be revocable? Because the entire commitment transaction can, in fact, be updated, at any time. The HTLC may be absorbed into another output. It may time out and be absorbed into the originator's output, et cetera, et cetera. So in order for the entire commitment transaction to remain revocable, remember, the outputs to the local node are in the revocable sequence majority contract. This output is revocable with the revocation key. And we need to introduce a way for the HTLCs to be revocable as well, okay? And that's what we're doing here. So for peer A, who is now forwarding the amount, the HTLC timeout spending scenario, the HTLC timeout scenario, let me say that again. So the entire HTLC output can be revoked with a third spending condition. This third spending condition is spendable with a private key R. And to give the counterparty time to actually to perform this revocation, there's now a delay that's introduced to the HTLC timeout spending scenario. It's the timeout scenario because that's the scenario that spends to the local node. Here is peer A. In the second case, the local node is peer B, and so the delay is introduced for the spending scenario, which spends to the local node, namely B. And again, we have the same revocation clause as we have above. It's spendable with private key R. Okay, so somewhat convoluted, but these are the things that allow us to make the HTLC revocable, in addition to be able to hash lock funds and timeout after a certain period. Okay, if we use this design, let's consider what would happen. So, peer B has a revoked commitment transaction. Note the revoked outputs here in orange. It is not a valid state, but peer B broadcasts it nonetheless. Now, given that it's revoked, these are revoked outputs, peer A will be able to spend them immediately, right? So peer B can't spend it because there's a certain delay that's being enforced, but peer A can spend it immediately. So that seems to work fine, right? Let's consider what happens if a valid transaction is broadcast. So this is not a revoked transaction, it's valid. B wants to close the channel, and B has the pre-image to HTLC. So there's B wants to close the channel, and B wants to spend or sweep the HTLC B here. What happens is, if the timeout occurs before the delay, this HTLC amount will be returned to A, even though B may have a valid pre-image, right? This can occur. Timeouts generally want to be short. Delays, we generally want to be a little longer. We want to give people time to sweep revoke transactions. And the timeout, we want to be relatively short so that the that the payment routing doesn't take too long, right? Okay. So B has a valid preimage, and in theory would be have the right to spend this output here. It's not a revoked output; it's a valid state. But because the timeout occurs before, A can spend this this HTLC before, because the timeout occurs somewhere here. Now that's a problem in our design. In our design, the timeout can only occur after the delay. So there's a certain coupling between delay, which is related to revocation, and timeout, which is related to the time we want to give the participants to route the funds through the network. And the way we solve it is with a two-stage transaction design that we use in Lightning. So the revocable output is now moved from the HTLC to a child transaction that has a regular RSMC output where the revocation occurs. So the delay that we had before is now moved to this output script. And that allows us to decouple the timeout and the delay into two different transactions. These two transactions are coupled because this is the child transaction spending from the parent transaction, okay? And we do the same for both sides. For the receiving node, it's obviously the success condition that the child transaction spends from, right? The success condition together with the preimage. And we can see here, we have Yep, go for it.
So, did I understand it correctly that we broadcast two transactions, the parent transaction and the child transaction?
Correct.
I could see in a block explorer two transaction, right?
That is correct.
Okay, great. Thank you.
That's correct. So when you close a transaction and if you close a channel and your channel still has HTLCs which are live, then the HTLCs will be spent by a child transaction like this. So it's either a timeout transaction or a success transaction.
Okay, yeah.
Yep.
Exactly. Yeah, there was a discussion online related to that if those amounts are really small, it will be hard to put them on chain because this HTLC transactions amounts can be really tiny.
Exactly. Absolutely. I don't have any material on it, but one idea to solve that problem is to create additional outputs. So you could have like an initial output that spends to B, but has a zero amount. And so what that allows you to do is you can then, if the fees are too low, or the amounts are too low to include reasonable fees, you can add another child transaction that has higher fees, and the mempool will accept both transactions because on average they will have a relatively high, they will have sufficient fees. So that's called child pays for parent. You've probably heard of it before, but the child pays for parent policy in the mempool allows us to add a child transaction that pays the fees of the parent. So that's something that they want to add to the protocol. But it requires more interactivity from the node side, obviously. So, but it's definitely possible.
Okay, another question, but it's more hypothetical. Is it possible to put a child transaction into a parent transaction? So you have the parent transaction at index 0 and the child transaction at index 1?
Yeah. You can have one parent and multiple child transactions that spend outputs from the same parent.
I mean in one transaction. So there are not two transactions. So the index 1 refers to the output of index 0 in the same transaction.
That you cannot do. That's an interesting idea, though.
So you can
you want to spend in the same transaction.
Yeah, so I can save one transaction.
You can't do that. That's an interesting idea, though.
Okay.
That's an interesting idea.
Okay, sorry, it's just hypothetical.
Yeah, no, I'm thinking out loud. Like, why would it be not possible to do that? And I can't think of a reason why that would not be possible. Other than obviously it's not part of the protocol, but
maybe I should request.
You should
pull request.
Probably should. Yeah, you should write a book about this. All you would need really is I'm thinking out loud here. All you need is a flag somewhere that tells the validator or the validating node that, hey, I'm spending from the UTXO that's in the same transaction, right? Because the validator will always look for a UTXO in the index, or the lookup in its table. And if it doesn't find the UTXO, then obviously it's not a valid spend. But if you have some flag that says, hey, you don't need to look in the UTXO, you need to look also in the same transaction itself.
So, and could it be possible? So the input has to refer to the transaction ID. The transaction ID is still calculable.
See,
I can calculate the transaction ID.
No, you can't, because it becomes a circular dependency.
Okay, so it's not possible to.
You would have to include some kind of flag that says.
Yeah. Okay. Mm-hmm.
Yeah. The other thing is, like, you don't solve the fee problem necessarily that way, because, right, separate transactions are signed at separate times. So how should I say that? So let's say you have a fee problem because your fees are too low, and the fees increase over time, but then you want to broadcast your old transaction that you previously signed. You want to create a child transaction, because there you can then assess during signing, before broadcasting, what a good fee will be. Right? Like, the point of having child transactions that you can hook on later on is that at the time of hooking on the child transaction or signing the child transaction, you have an up-to-date view of what the fee rate is in the mempool, which you didn't have when you were signing the parent transaction.
But I can add in a new input and a new output. So, and the different could be the difference could be different if I add a new output. I could add a new output, which is mining fee. I think we did discuss it in what was it? SigHash. No, SigHash.
No, I see.
Everybody can spend.
But you're suggesting that the parent transaction, be be re-signed, right?
Yeah.
You would have to re-sign the parent transaction.
Yeah, maybe.
And so that's possible. So the two peers can renegotiate that commitment transaction. But what if another peer doesn't want to do that? What if the other peer goes offline, right?
Yeah.
So there's no guarantee that you can renegotiate that fee. However, if there's an output that you can hook a child transaction to, that child transaction is controlled entirely by you, and so you have, there's nothing that can prevent you from doing that.
Okay.
Yep. Okay. Yeah, so this final slide just demonstrates how this works. So we have a invalid commitment transaction that's being confirmed that is spendable by the success transaction, right? That's the child transaction that we had here previously. And because this is a revoked output, the output of the success transaction will also be revoked, okay, with the same revocation key. And there's a delay. So this party B cannot spend until after the delay, but because it's revoked, party A can spend it immediately, right? So that's how the child transaction, the two-stage HTLC design works. Same goes for the other side. After a timeout, the timeout transaction can be signed, as can be broadcast. But because the output of the timeout transaction is invalid, party B can sweep this output immediately. Okay, so let me just quickly jump to the funding of the channels. Antonio, I know you asked a question at the beginning. So for single funded channels, the channel opening is pretty straightforward. So these are the messages that A and B need to exchange in order to negotiate a channel. In this case, only one party funds it. So 3 things need to be created: the funding transaction, the first commitment transaction for peer A, and the first commitment transaction for peer B. The funding transaction only has one input, and the input is provided, or one input from one party, and that's provided by peer A. So what we need to do at the beginning is we need to exchange the information. Peer A needs to provide the TXID of the funding transaction to peer B, so that peer B can create the commitment transaction and sign off, right? And peer A can do that before the transaction is signed, because it's a witness transaction and the input script is not part of the TXID. So both parties sign both commitment transactions, and the funding transaction is not signed yet. So at this point in time, there's no risk. Because the funding transaction is not signed, nothing is at risk. No funds are at risk. So if peer A becomes unresponsive, both parties can just walk away. Peer B doesn't care if the funding transaction is then suddenly broadcast, a long time later, because peer B has no funds at risk. Okay, so that's what makes single funded transactions relatively easy to implement. There's no, if the funding of the channel fails, peer B doesn't have to take any action in that sense, right? So as you see here, if the broadcasting of the funding transaction never occurs, B or P doesn't have to take any action. If it does occur, great, then the channel's open and peer B can receive funds from peer A. Okay, so dual funded channels. How would it look like if we created dual funded channels? So in this case, we have to create a funding transaction which spends UTXOs from both parties, both A and B. And so peer A needs to exchange that information with peer B, and peer B needs to exchange that information with peer A. Okay, so once that information is exchanged, all 4 transactions here can be constructed and they can be signed. We also have these change outputs here, right? Because the UTXO that funds the funding transaction may not have the exact amount. So peer A needs to sign its commitment transaction and also the commitment transaction of the remote peer. Peer B needs to sign the local commitment transaction and the commitment transaction of the remote peer. And they exchange these 2 signatures. So at this point, nothing is at risk. No funds have been committed. No signatures for the funding transactions have been created. But the commitment transactions are ready to go. They're signed. And what we need now is we need both parties to sign their respective inputs for the funding transaction and exchange them. And that's where it gets a little tricky. So it can occur that one party has received both signatures but has not shared the signature with the other party. So in this case, peer B has received signature A. It's obviously got signature B because it's signed itself. And peer B is in the fortunate position to be able to broadcast funding transaction by itself. Peer B may not share its signature with peer A. So this becomes problematic because both peers have funds at risk. Both peers have provided a UTXO and signature. However, only one peer can actually broadcast that funding transaction. So in the case that peer B becomes unresponsive, what does A have to do? What do you guys think? So peer B has the funding transaction with both signatures, and peer A has a partially signed funding transaction, which it cannot broadcast because it's missing signature B. Any ideas?
Is the funding transaction B confirmed yet?
No, it's not confirmed.
Okay.
It's not confirmed. But it's the only funding transaction that's valid.
Do they have their commitment transactions already or not yet?
They have the commitment transactions ready. Everything's ready to go. Everything's ready to go. The only thing that's missing is peer A does not have signature B for the funding transaction. Peer B, though, can broadcast the funding transaction. So what's the risk for peer A? Okay, so the risk is the following. Peer A cannot assume that the output A, so let me put it away. The problem is peer B can broadcast this transaction anytime. Today, tomorrow, in a year's time. So that can be disruptive because this out point that peer A provided for the funding transaction can potentially be spent without peer A knowing it. So to be safe, what peer A wants to do is if peer B suddenly freezes in this part of the channel opening stage and peer B never broadcasts the funding transaction, peer A needs to sweep this out point A to prevent B from, sorry, let me say it again. So peer A needs to sweep or spend this out point A so that this funding transaction becomes invalid. It becomes invalid because this out point A is then spent and this funding transaction will be double spending this output. So dual funded channels are not impossible, but your implementation needs to catch a scenario where the remote peer has the entire funding transaction. That funding transaction is then not broadcast, the peer freezes, and your local peer needs to then sweep the out point that was funding the funding transaction in order to prevent this funding transaction to be broadcast some unknown time in the future.
So is it possible to work within a log time or time log? So if peer B don't spend the funding transaction after a certain amount of time,
yep,
the spending goes back to peer A. The output goes back to peer A, or the funding transaction gets invalid?
That's a good question. Let me think out loud. It is possible to create a delay so that a spend cannot occur before a certain time, but it is not possible directly to create a time lock mechanism that returns the funds after a certain time. You know what I mean?
Yes. Yeah. Okay. So and then if I, yeah. So.
Right. So I can do something like a hash time lock contract, but yeah. I would have to spend the output. I need to actively spend that output, so it'd be the same. Right? Like my output point A here could be a HTLC.
Yes.
In that sense, something like an HTLC. So it either times out. It either times out or I can spend it myself. But I still have to spend it myself after the timeout.
So it's not possible.
I still have to act, right? If peer B becomes unresponsive, I still have to act and broadcast a transaction to make sure that this output is spent.
So it's not possible to create a condition that B has to provide another secret after amount of time. So maybe after a minute, for example, B have to not provide the signature of A. have to also provide a signature C maybe, or a key R or something like that.
Yeah, I think what you want is you want a signature A that expires. That's what you want.
Yeah, yeah.
Right.
Yeah.
And so that doesn't exist. You can have a transaction that is spendable after a certain time, but you can't have a signature expire in that sense. If you had a signature that expired, actually, let me think. Pierre, I'm not sure. Maybe there is a way. I need to think about that.
So I mean, I have the condition. We have block height 100,000.
Yeah.
For example.
Yeah.
And I have the condition after if block height 100,001 occurs.
Yep.
You have to provide signature plus secret R, for example.
Yep. That could actually work. So your out point here, the output script here, requires just the signature, or after a certain block height, an additional argument. But there is no opcode that can directly check for block height.
Okay, yeah.
That's the problem, because you need to find a way to obtain the block height onto the stack, and you can't do that.
I can, because I can check the block time in the past. I think this is what check block time do maybe.
There are only two fields of the transaction that you can check from the script machine. One is the lock time from check lock time verify. The other one, the sequence field, check sequence verify. There is no way for you to check the header data in the Bitcoin script. That does not exist. That I know for sure.
Okay.
There are ideas where you can check other pieces of transaction data on the Bitcoin strips, Bitcoin machine stack. Check sig from stack is one idea. It's not implemented. There are a couple other ideas there where the script machine can check for not just the time lock and the sequence, but other parts of the transaction, even the output.
Okay.
But yeah, I mean, really good question. But no, there's no way for you to check the block height from the script machine, and that's what you would need.
Okay, thank you.
I mean, you can. That's another BIP you can maybe author, like another check sig.
Yes, yeah.
So you got two ideas now. That's awesome. That's really awesome. But if you had that, yes, you could prevent the signature from being valid after a certain height. So now we have to actively spend it, but in your case, you can make that an automatic mechanic.
Okay, thank you.
Really cool idea. I like it. Okay, Antonio, did that kind of answer your question? I hope.
Yeah, that was great, James.
Awesome.
Just
awesome.
One extra question.
Go for it.
It's about the revoking your RSMC outputs, and I think it goes for HTLCs as well.
Right.
It says you do that by sharing your secret with a counterparty.
Right.
And how does that? How do you do that? How do I see that?
It just happens through the messaging protocol. So it's just a P2P off-chain message, through the P2P network. There's another, I forget the name of it. There's another P2P protocol for Lightning as well, messaging protocol.
Okay, so that's a separate P2P message.
Yeah.
Is there a bolt on that, or is that
there is a bolt on that?
And, okay,
I forget the number, but there is a bolt on that. Yeah.
Okay, thank you.
Yeah, cool. Okie doke. I got one more slide. I think that's worth looking into. Okay, we got 15 minutes left. Sure. Okay, so as we mentioned before, these commitment transactions have a certain fee implied. And the problem with the commitment transaction is they are signed at a certain point in time, and perhaps you close your channel at a very, maybe days later or maybe a week later, and it can happen that at the time of closing, that your commitment transaction has a fee rate that is just too low. It won't be confirmed because there are other transactions that'll be included in the block instead with higher fee rates. The one idea is to create child transactions that can spend from specific outputs. And you can create a child transaction with an arbitrary fee rate, thereby lifting the average fee rate of both transactions towards the top of the mempool so that it can get confirmed. But that will require these output hooks. The Lightning guys call them hooks. That's the term they use. That's just an output that's spendable by both peers. And so that's something that they want to introduce that doesn't exist today. But that would solve the fee problem in that sense. And today there's not bizarre, but there's a inconsistent policy, mempool policy that makes that creates a problem with introducing child transactions that bump the fee rate. So, for example, what can happen is you can have a perfectly fine commitment transaction, and an adversary can hook a transaction that actually has a very low fee rate. So fee rate is satoshis per virtual bytes. And this child transaction actually has a low fee rate, thereby dragging down the entire average fee rate of both transactions downwards. And now you've prevented this transaction from confirming. And it's then pretty hard to bump this low fee rate child transaction because its fee rate might be low, but its absolute fee may be very, very high. So that's an attack vector that needs to be solved. That can be solved quite easily by just adjusting the transaction bumping policy. So today, the absolute fee rate of the replacing child transaction would have to be higher, which is absurd if this child transaction is a very large transaction. Instead, it should be the fee rate that needs to be higher. But this policy was created in a time where blocks were empty, and absolute fees were more important than fee rate. So the satoshis per byte. When blocks are full, you don't care about absolute fees. You care about the fee per byte. You want to maximize your block reward, right? Okay. And in a world where we need to add these hooks and child transactions, we also need to find a way to be able to propagate these parent-child transactions over the P2P network. We need to be able to propagate them together, because what can happen is a parent transaction may have such a low fee rate that it by itself will no longer be accepted into the mempool. So if it's not accepted in the mempool, it's not relayed to the next node. And the child transaction will not relay either because it's spending a UTXO that doesn't exist in the mempool yet. So the idea is to relay transactions in multiples and packages where the ancestor is also included. And so this would be a new P2P network message that's required, or a new relay policy that's required. And so that's something also that's being worked on and will be required. So the aggregate of these ideas or these problems reflect the ability to close transactions when we need to. To close channels when we need to. If there's a risk of closing channels, obviously that means the balance of these channels are at risk. So that's obviously a problem that needs to be solved. Okay, so there's one more part that I wanted to add, and that's regarding submarine swaps. Let me just share that real quick. So I drew this up this afternoon because submarine swaps have been in the news again recently with Lightning Labs introducing them as a way to obtain liquidity. So Antonio was talking about having only outbound liquidity. So if Alice, let's say Alice has a channel with Bob, and Alice has already emptied all her liquidity on her side. She's been buying stuff, and all these transfers are going outwards to Bob. And so Alice is now out of funds, and she would have to create a second channel to Bob again, fund a second channel to Bob again, or close this channel and open a new one. And she doesn't want to do that. And a way to solve that is with submarine swaps. So a submarine swap is nothing but I pay you funds on-chain, and you pay me funds off-chain through the Lightning Network in a way that is atomic, so that the swap will either go through or not at all. So both payments on and off-chain will have to go through together, or both will fail, right? So that's what we're trying to achieve. So let's look at the first step. So Alice needs more outbound liquidity to Bob. She's spent all her liquidity already. And there's a third party, Charlie, that is willing to provide that liquidity via submarine swap. And so Charlie will need to do two things. Charlie will route funds to Alice. And Alice will send funds to Charlie on-chain, right? So it's a swap. One transfer is off-chain, one transfer is on-chain. For Alice, so for this to work, Alice sends Charlie an invoice. And with an invoice, Charlie then can construct the route. All the HTLCs on-chain will be constructed with the same payment hash. Now, very important, since Alice has the payment hash, she generated it. Alice will now send the on-chain funds to Charlie, also with an HTLC. However, this is a confirmed transaction. Remember, these HTLCs are all non-confirmed, right? They're signed, they're stored locally, but they're not confirmed. Alice now sends, signs, confirms, has a transaction confirmed with an HTLC that spends to Charlie, and which is unlockable with a pre-image to this payment hash. These payment hashes are identical. So if the routing now is successful, the pre-image needs to propagate backwards to Charlie, right? If the pre-image propagates back to Charlie, that means Charlie has forwarded the amount successfully, right? So Charlie is down the amount that's forwarded. He's down that amount. However, he's gained this pre-image. And with that pre-image, Charlie can now spend this output that has been confirmed on-chain, right? So if the routing does not complete, then these HTLCs will time out. Charlie never attains the pre-image, but Charlie never has to forward the amount. And this output here will time out and then return to, can then be spent by Alice, right? So again, it's a swap between on-chain funds and off-chain funds. And this way, I can always have liquidity either being routed to me, or I can reverse the scenario where I want to route liquidity away and obtain on-chain transaction, an on-chain output in return. That's also possible. So you can reverse the roles of Alice and Charlie, and the liquidity situation is just the reversed. Yep. Does that make sense? So this is submarine swaps. It's a pretty neat idea, and it's a way to manage liquidity if you run out of funds on the network. However, it does require one transaction on chain, or actually it requires two transactions on one chain. This is one transaction, and the spending of the HTLC is the second transaction. So there are fees involved. But yeah, that's how it works. Any questions? All clear? Okay, guys, I'd be done for the session today. We have one more session on Monday. I would suggest that we use it as a review session. So if there are any topics you guys want to cover, just post into Slack. Otherwise, I can propose a list of topics I think are worth reviewing, and then we'll do that on Monday.
Hey James, just sorry to I was kind of thought of a question.
No worries, man.
Give this example of script related to this RM. What is it called? Those locked.
Oh yes, I forgot to show HTLCs.
For HTLC, is there like an opcode script we can see? I mean, it's just for me. It's
easier
to see.
The HTLC is a masterpiece in Bitcoin scripting. I forgot to show it. I'm sorry, but here it is. So there are two types of HTLCs. There's the HTLC sent and the HTLC received. This is the same.
I think you have all the Submarine Swap page.
Oh, I'm sorry. There you go.
Yeah, fine. Yeah,
okay, cool. So we have HTLC sent and we have HTLC received, and it's sent or received depending on whether the HTLC, if you are the person receiving the HTLC or the person, if you're receiving the forwarded funds, or whether you're the node that's forwarding. So that's how it's described, okay? And the HTLCs will obviously be asymmetric. They'll be different. So this is the HTLC sent, and there are 3 spending conditions. There's a timeout. So either the output is spent by timeout, either it's spent by the pre-image and Charlie's signature, or it is revoked. And as you go through the slides here, Dimitri, you will see which part of the script is executed for each of these spending conditions. And it is one complicated output script, but it's an incredible design.
All right, that's cool. Thanks so much.
It's a really cool design, and I'm not sure how they. Yeah, I'm not sure like what is the best practice method to actually translate. You know, let's say you know what your script wants to do. You know the spending conditions, and how do you translate them into the most efficient output script? How do you compile that into the most efficient output script? That's a question I can't answer. I think that's just all manual. Yeah. So that's received, and received will look like this. Again, success transaction, Bob signature after timeout, and verification key. This is all in the payment channel slide deck. So I encourage you to check it out if you have time. Okay. Guys, thanks a lot. I hope that was good for you guys. And again, let me know what you guys want to review next time. I'm happy to do it. Or if there are other questions you want me to cover, I can spend some time to prepare for that. And otherwise, I will see you on Monday. Okay? Cool. Thanks, guys. Have a great weekend. Thanks, Pierre. Bye, guys. See you, Matt.